Hello, check. Hello.
Okay, are there questions? Okay, so let me begin. So yesterday we showed how to covariantize half of the Maxwell's equations, right? The source-free ones. So today we are going to discuss how to covariantize the other half, which are more involved. So let me remind you what the other half of the Maxwell's equations are. So again, in absence of gravity, write this. We have where this is a source. So J is a vector whose zeroth component and there is a spatial component. So this has the interpretation of being charge density. And this is the current density. So let me just verify that this gives the correct equation that you are familiar with in the non-covariant formulation. Okay. So I can rewrite this as okay, all I have done is that I have just explicitly summed over this mu nu index. Okay. So when mu and nu are 0, 0, you get a minus sign from here. That's this term. Okay. And when mu and nu are spatial indices, there's a delta ij, Kronecker delta. So that's why you get this term. Is clear? Minus sign of the first equation. That may be because of the convention. Then we'll see if it agrees or not, right? What we use. Yeah. So this is the spatial component, the space component of the. Oh, this is J. Okay. Yeah. I mean, for J0 is it's this the 4 vector J. Okay. Pardon? Yeah, exactly. Eta is a minus 1, 1, 1. Okay. So here, if we take rho equal to 0, okay, then if I0 we know is electric field, right? That's what we had defined it last time. So this equation, and this is 0, right? Because F is antisymmetric, so F00 is 0. So this becomes, and here if rho is 0, right? Eta 0, 0 is minus 1. Okay. So you get plus J0. Okay, so this is the divergence of E equal to rho, that Gauss law, right? Divergence of E is equal to the charge density. That's what this equation represents for rho equal to 0. Is it clear? And now we'll take rho equal to J, one of the spatial components. So we get derivative of Fij minus time derivative of F0j. Okay. And this is minus eta j k j k. So that's minus j j. Here I'll just write upper index because now it doesn't matter anymore. We are doing in flat space and we have chosen particular space coordinate. So let's see if we can interpret this equation. So F0j is minus Fj0. So that's minus Ej. Right? Where F is antisymmetric. And this one is so I can write this as minus because epsilon is antisymmetric, so I just exchange J and I. So this is the jth component of curl of B. Right? Ik and derivative of B. So this is the jth component of curl of B. So this equation basically reduces to curl of B plus the jth component of this equation. Okay, there are a minus sign, right? Everything is minus in the way I have written here. Everything would have been minus, right? But that's the other Maxwell's equation. I think I've got the something is wrong. Pardon? Yeah, thank you. This should be plus, right? Because there's a minus sign here, so this becomes a plus sign. Okay, so you can write this as curl of B minus. Okay, this is just to convince you that this equation that I have written here in the Lorentz covariant form represents the usual Maxwell's equation, the ones that have sources. Okay, either electric charge density or the current density. So our eventual goal will be to try to make this into a covariant form, general coordinate invariant form. Right? That's what will describe the second set of Maxwell's equation in presence of gravity. Okay. But before that, we have to learn something about this J, right? Because you have to learn how to covariantize J. Okay. This we know already because we have already declared that in card space, right, in general coordinate system, this transforms as a rank 0 to tensor. Right? That we cannot change anymore, right? Because we have used it already in our Lorentz force law. This one we don't know what it will be, right? We can claim that it will be a charge rank 1,0 vector, okay? But we have to first understand what this object is. Okay, then we can try to study what it does. Is it okay? Are there questions? Okay. So now let me write down the expressions for J mu, right? Still in absence of gravity. And when you say what is J mu, what I have in mind is that what is J mu in the presence of a collection of charged particles. And these could be moving. So what we are going to do is to write down first the expressions in non-relativistic notation, right, which may be more familiar, and then try to convert that to the spatial relativistic notation, and then eventually you have to generalize it to general coordinate system. Okay, but first let me write down the non-relativistic form of what these J's are. So J0 xt will be sum over n. Okay, this is sum over all the charged particles. En is the charge carried by the nth charged particle. Okay. And then delta cube of x minus x of t. The charge density is where the charge particle is. Right? That's what this delta function is telling us. Right? And it's time dependent because the particle may be moving with time. Velocity doesn't enter the definition of the charge density. Right? The velocity will come in the definition of the current. Is this clear? Right? Delta cube. This is a Dirac delta function. Right? So the point is, if the charge is placed at x naught, then the charge density is delta cube x minus x naught. Right? That's what we are using, because in integral of this should be 1 then, right? It should be localized only at the place where the charge is, right? And its integral should be 1. Right? That fixes this to be the Dirac delta function. Because it's a vector, right? So there are three, it's like product of 3 Dirac delta functions, right? Maybe it will be important, so let me write this here. So this is by definition delta x1 minus x1 of t, delta x2 minus x2 of t, delta x3 minus x3 of t. And that's what we mean by this 3. Now, what about Gi? It will have a similar form, except that it will be also multiplied by the velocity of the particle, right? Because it's current. So it will be En. Sorry, this is xn, right? Nth particle position. dxn I dt. Is it clear? So the first goal will be to write this in a covariant form. Right? We are not going to change the expressions. It's the same. This is correct, right? But this doesn't look covariant, right? Because you are giving spatial roles to these 3 of the coordinates, right? And not the time coordinate, right? So time and space appears asymmetrical in this form, right? Even the way we are specifying the trajectory, right? X vector as a function of t is not the covariant way of specifying the trajectory, right? The covariant specification will be in a parametric form. Okay? So in the covariant notation, the trajectory is of the form is x mu of u. Not really, right? Unless you put additional restrictions. At present, the parameter is completely arbitrary, right? We are not even demanding that it's affine, right? What we saw in the case of particle trajectory that we discussed earlier, that you could start by saying arbitrary parameter, right? But then it helps in writing the equations if you choose u to be affine parameter, right? Where equal length of u corresponds to equal distance in space. We are not demanding that right now, right? Later on, you may want to restrict u to affine parameter, but right now it's completely arbitrary. Exactly. It's just a way to relate the 3 coordinates in terms of the 4th one, right? Once you eliminate u, right, you can use say the x naught of u equal to small x naught to write u as a function of x naught, and then substitute in the expression for the x size to get xi as a function of t. Right? That will give back these trajectories. Exactly. It can be eliminated eventually, right? If you want to get the 3 in terms of the fourth one. Right? So this is not even related to relativity, right? Just any curve in, say, n-dimensional space. Right? You can specify it by saying that n minus 1 of the coordinates are specified in terms of the last one, nth one. Or you can say all the n coordinates are specified as a function of some parameter on the curve. Yeah, these are just 2 different ways of labeling the curve, right? The first way is more efficient, that you are not introducing any additional parameter, but the second way is more symmetric because you are not giving spatial role to any particular coordinate. It's okay? Okay, so now the claim is that in terms of this parametric form, we can write down a covariant expression for J mu. Again, covariant in this case means Lorentz covariant. So J mu of x, where x now stands for x and t, is given by integral okay, I'll write a simpler form. Maybe I write the most general form first. It's okay. So here I have taken different trajectories to be labeled by different parameters. It doesn't really matter because this is the integration variable, right? I could have used the same parameter label. Xn, thank you. Then I have this dxn mu du, then, and then there's a 4-dimensional delta function instead of a 3-dimensional delta function. So in this form, we can see that there is no spatial role that any particular coordinate plays. Right? All the coordinates are on the same footing. Is it clear? X is a point in space time now. Right? Here you are writing as x and t. Now x is a point in space time. The question is this true or not? Right? I have written down an expression. Right? This is the same as what we had earlier. Because we will try to verify this first. Right? It's covariant form, but we have to make sure that it's the same as what we had. Right? We are not changing the theory. But is this form clear? Okay. And just to avoid clutter, I may later on drop this index u, n from u, right? Because it doesn't really matter. Independently, you can parameterize by different parameters, but or you can say that the same parameter labels all the trajectories. Okay, it's just an integration variable anyway. So to do this integral and to show that it reduces to what we had here, we are first going to actually do the u integral. And we will do the u integral using one of the delta functions. Right? There's a delta function here, right? So we can always do the u integral. And the particular delta function that we're going to use in order to make connection with this is the x naught. Right? So you use x naught to do the u integral. Is it clear? Now we have to use one further information. That x naught of u increases monotonically as function of u, and as u goes to infinity, x naught of u goes to infinity, and as u goes to minus infinity, x naught of u goes to minus infinity. Okay, this is true for a physical particle trajectory, right? U monotonically increases along the trajectory, right? And for any physical particle, the time coordinate will also increase monotonically along the trajectory, right? You cannot go backward in time, right? This is actual physical particle that is moving. Okay? So x naught of u is a monotonically increasing function of time. Okay? And if you take the whole trajectory, right, it must have started from minus infinity. You can always take a particle trajectory and extend it back to minus infinity and extend it forward to plus infinity, right? So that's why we have these conditions. So under these conditions, this one of the delta functions x naught equal to x naught of u has a unique solution for u. Okay, let me put the un here because it need not be the same un everywhere. Okay, that is say t. X naught is what I'm calling t. So un is a function of time. Right? When you solve this, you get un as a function of time. So using that, you can do this this un integral because there is a delta function, right, which sets x naught of un to time. Right? So you are trying to do this integral dun delta of xn naught of un minus t. T is x naught. That's one of the delta functions here, right? So you know the result for this? 1 by derivative of x naught, right? So at u equal to, let me call this u naught. So unique solution for u, sorry, I shouldn't call u naught, let me call this what? F of t. Fn of t. Right? Wherever the un, x naught of un becomes t, right, that determines un as a function of t, that's what I'm calling Fn of t. So it has to be evaluated at u equal to Fn of t. To this equation, exactly. That's the solution to this equation. That's where you have to evaluate this. So now let's go back to J0. So you try to calculate J0 from here. So J0 of x, now u integral is gone, right? So sum over n, En. This one has to be evaluated at the solution. Because un has been integrated and un has been set equal to some particular value. Of this 4 delta functions, there are 3 delta functions still remain. And then from this we get 1 over So all of these have to be evaluated at un equal to Fn of t. Right? This one, this one, this one. Everything has to be evaluated at un equal to Fn of t. This one, right? Exactly. So that's what I'm substituted explicitly. But this has to be evaluated at the value of un that the delta function picks up. See, I'm using the fact that integral du f of u and delta of u minus Fn of t, let me call it a different function, is f of u evaluated at u equal to Fn of t. Right? So this was f of u was this object over here. Right? I have to evaluate at un equal to Fn of t. Right? Similarly, the other three delta functions all have to be evaluated by setting un equal to Fn of t. Zero, yes, thank you. Because you are calculating J0. Okay. So now you see that these two cancel, right? And now xn of un, right? We have to substitute for un Fn of t. So it becomes the old trajectory, right? What we are calling xn of t, because you are supposed to eliminate un, right? And that's what is supposed to reproduce the old trajectory. So this thing is, let me mark the cancellation. So these two cancel. And you use the fact that delta of x minus xn of u at u equal to Fn of t is nothing but delta of x minus xn of t. All we are doing is that instead of using the function of u, we are expressing this in terms of function of t, right? By eliminating u as Fn of t. That's what that was original trajectory was, right? So you get sum over n en delta q x minus xn of t. Okay, and that's exactly what was our J0. Yes, indeed. Because if it was not monotonic, right, then there might have been more than one solution. Right? And you have to add up the contribution from all those solutions with sides. Right? So the fact that it's monotonic is important. Right? That is a unique solution. This Fn of t is unique. Right? That's why I am using the fact that it's monotonic. Is it clear? So now you can easily see what happens to the i's. Right? Here, if you say mu equal to I, right, you get dxn I dun, right? And what is in the denominator is dxn0 dun. Right? That is basically dxi dt. Right? By chain rule, we are writing u in terms of t. So let me write here. So ji of x from the same formula will be sum over n en dxn I dun at un equal to Fn of t. Okay, this thing remains the same, delta of x minus xn of u, and then 1 over okay, so this ratio becomes sum over n dxn I dt. Okay, after we eliminate u, and then there is a delta cube of x minus. Is it clear? Right, because this is measuring the change in xn against change in xn0. Right? Change in x and 0 is a change in time coordinate t. Okay? So that's why it becomes dx and dt. And this is exactly the non-relativistic form that we had. Other questions? Okay, so now we'll check some consistency conditions of this. It looks like we are doing a lot of things on electrodynamics, but ultimately you are going to use all this insight to for gravity. Okay, when you try to write, for example, the equation that determines the gravitational field in terms of sources, right? You are going to use all this insight, right? But right now we just think of this as writing electrodynamics in the covariant form, because we want to use this to write the electrodynamic equations in the presence of gravity. Okay, so let's go back to the equation again. Okay, so we had eta mu nu f nu rho as minus eta rho kappa j kappa. Okay, so these I'll write in a slightly different way as eta mu nu eta sigma rho this gives you Kronecker delta, right? Delta rho sigma, sorry, delta sigma kappa. So this gives you minus j sigma. Okay, so this is the Maxwell's equation written in covariant form. Now let's calculate so this I can, okay, let me write, just rearrange things a little bit. Okay. This one is antisymmetric in nu and rho, right? F nu rho is antisymmetric in nu and rho. So when you raise it, raise the index using eta, this is antisymmetric under the exchange of mu and sigma, right? Because you raise nu by mu and raise sigma by rho. Okay, this is anti, so so then this can be written as del f sigma mu is just raising by the etas. This is antisymmetric in sigma and mu. Okay. This, on the other hand, is symmetric. Is okay? So this was vanish. Right? Is it okay or no? Right? All you are saying is that if you take the left hand side of the second set of Maxwell's equation, okay, and put another derivative, right? with the and contract with the free index, which in this case is the free index is just okay. After you have raised it, the free index is sigma. Right? Just contract to the free index. You get a derivative, two derivatives which are obviously symmetric under rho sigma exchange, and on the other hand, this contract to F is antisymmetric under rho sigma exchange. So this must vanish. Okay. So this shows that for consistency, this shows that for consistency, this should also vanish. Right. Again, this is something you probably have seen as charge conservation, right? This in the component form is okay, which basically says that the charge is conserved, okay, because if we integrate it over any volume over some region, this is minus which is minus integral j dot ds. Okay, surface integral. Okay, so this is saying that the rate of change of charge inside a given region is minus the rate at which the charge is flowing out through the surface. Okay, so there is no net charge violation. That's what this implies. Okay. But the point that I wanted to emphasize here is that it was not possible, right? Okay, charge is conserved. Okay. But could you have written a Maxwell's equation with a non-conserved charge? Okay. And it wouldn't have been possible, because if the right hand side has this vanishing, right, then just for consistency, it better be that the whatever appears on the right hand side, okay, has this property, that it should be a conserved charge. Is this clear? We can in fact give a derivation of this in more general theories, okay, just from gauge invariance. Okay, so let me describe this, because again this insight will be something that will be useful in gravity. Okay. Suppose we didn't know the Maxwell, the left hand side of this equation, okay, but we knew that it comes from some variation of some gauge invariant action. Okay, so suppose the Maxwell action. So let's suppose the action involving mu, just mu, is integral of something of some Lagrangian density, d4x, where all we know about this Lagrangian density is that it's a function of f mu. Okay, in the Maxwell theory, it will be f mu square of f mu, but in a more general system, okay, it could involve, say, quartic term involving f mu, right? F mu square, and so on. Okay, anything, we don't care what it is. And then to produce a source term on this side, then we can add integral mu j mu. d4x, thank you. So let's look at the equation of motion, right? How we derive the equation of motion. We say delta S. The first term we write as integral d cube x, sorry, d4x, delta mu times something. Right? This something is what is appearing here. But in a more general case, you don't know what this something is, right? So let's call it mu. And then by varying that, we will get integral d4x delta mu J mu. So this, and so this is equal to 0 for any delta mu. And this implies that we have the equation E mu equal to J mu. E mu equal to minus J mu. That is the equation of motion. And this is the way we normally derive equation of motion by varying an action. Right? You vary a field, and then you say that action has to be extremized. So the coefficient of delta mu has to vanish. The only difference here is that we have not said what L is. Okay, in the Maxwell's theory, L would have been F mu nu F mu. Okay, here I have not said what L is. It's just a function of F. E mu is whatever multiplies delta mu. So when you vary this L, right, it's a function of A mu, and you have to do all the integration by parts to write it as delta mu times something. Right? So this something, so E mu is, it depends on L. No, J mu is a source that may depend on other field, other objects, right? Like in this case, it depends on the particles. It may be dynamical, it doesn't have A mu. That's all we are using. Exactly. To get the A mu equation, you have to just vary A mu, right? We have to vary everything and get the equations, right? So for example, J mu, if we use this form, right? That form over there, or the more covariant form, which has gone behind. There, the dynamical fields are x mu, xn mu, right? So varying those, you will get the Lorentz force law, right? Because when you vary the xn mu, you will get some equation of motion for xn mu. Those will be the Lorentz force law. But those we are not interested in those right now. Okay, we are just interested in the equation that you get by varying A mu. So now the claim is that irrespective of what this Lagrangian is, this E mu satisfies the claim is that this is identically 0, irrespective of what L is. Here, of course, you saw this is identically 0, right? When you took the contraction with real sigma, you got 0. But what I'm saying here is without doing any calculation, you can conclude that whatever E mu you get, okay, whatever be the action, its divergence should be 0. Its force divergence should be 0. Okay. And the proof is simple. The proof is relies on the fact that if delta mu is the derivative of some function lambda, then delta L equal to 0, since F mu nu doesn't change. Right? F mu nu is, this is gauge invariance in the covariant form, right? F mu nu is this. So if you change A mu by a derivative of lambda, right, the derivative of lambda will cancel out. Yeah. So if delta mu is this, then delta L is identically 0. Right? Which means that here, whatever you get, whatever this E mu is, okay, integral d4x is identically 0. Because this came by varying L, right? Varying this integral d4x times L. So you can do the integration by parts. And this means that okay, and if this is 0, then the equation of motion, right, So now go back to the equation of motion. So equation of motion was E mu equal to minus J mu, right? This one, yes. This one? Oh, because you are varying this, we have assumed that L is a function of F mu nu only. F mu nu doesn't vary. So the variation of this is identically 0. Delta L is 0, right? And that's what is supposed to be delta mu times C mu. Yeah, boundary term you are throwing away. Here also you are throwing away boundary term, right? It's a bulk term that you are interested in. See, lambda of x we can take to be localized in a local region, right? Lambda is completely arbitrary up to us. Yeah, so the boundary terms you don't have to worry, right? Those can be made to made zero by taking lambda as appropriately. So what is the lesson? The lesson is that just as a consequence of gauge invariance, right? The fact that the Lagrangian for the analog of the Maxwell Lagrangian, whatever modification it may be, the fact that it's made of F mu nu only, we can conclude that whatever source you couple a mu to, better be conserved. Otherwise, you will not get a consistent theory, right? Because on the right hand side of the Maxwell equation, whatever you get by varying, whatever is the coefficient of delta mu, it has divergence free, right? Because the forward divergence of that is 0. So it better be that the left hand side has forward divergence 0. So it better be the right hand side also has forward divergence 0. Yeah, and that's necessary. Is this clear? Again, the reason that I am going through this is because you have to use these kinds of insights when you try to write down the equation for the metric, right? Because so far what we have been discussing is one side of general relativity, right? Which is that given a metric, how do various fields behave in that metric, right? The effect of gravitational field on the other fields. But we should also ask, right, that given these other variables, right, moving particles, electromagnetic field, what gravitational field does it produce, right? Otherwise, it's not, the theory is not very useful, right? Because if you give the metric, then I can tell you what happens, but what produces a metric, right? That also you need to learn, right? So that will be the second part of this analysis, okay? But it will use insights like this. Does it have to be when you do it in arbitrary metric? Well, it doesn't have to be because we'll use covariant derivative, and the covariant derivative of the metric is 0, right? So you can pull the metric through. Right? So I have not written down the covariant form yet. When you do that, right, we will see that we don't have to worry about this. Any question? Okay, so now I'm going to try to verify that this J mu that we constructed, the covariant form, this one, is really conserved. Okay, again, so far there is no gravity, right? I'm just checking the various consistency conditions of Maxwell's equation in the covariant form. So let's try to calculate this. So this is okay. I'm just going to drop the in from you. This is with respect to x, right? This is so first let's try to decide where is the x dependence in this expression, right? What should the derivative act on? Here, this is the only place where x is, right? Otherwise, there are particle trajectories, so we are not going to act on this. So this is going to act on this, and the mu for the particular mu, right, is going to act on only one of the delta functions, right? Because the first delta function has x0, the second one has x1, third one has x2, and so on. So only one delta function at a time it will act, right? So let me write this in a more explicit form. Okay, for this line, I'm going to drop the summation convention. I'm going to write everything explicitly. This one? Yeah, because this doesn't depend on small x, right? Small x is the space-time position, space-time coordinate. This is the particle trajectory, right? So the particle trajectory is an independent variable, right? And it's related to small x only through this delta function, right? So as long as you act on the delta function, we have got the x dependence. Okay, so the idea is that here mu was contracted, right? So there are 4 terms. Mu equal to 0, 1, 2, 3. Right? I have explicitly written out those 4 terms. That's why there is sum over mu. This runs over 4 variables. And for a given term, okay, only one of the delta function gets derivative. Right? That's the delta prime is the derivative with respect to the argument. Right? Only one of them gets the derivative. The other ones remain as normal delta function. Clear? This combination we can write in a somewhat simpler way. Right? Do you have a guess? Yeah, this is ddu of the Dirac delta function because delta prime is the derivative with respect to the argument, right? And the derivative of this with respect to u is sitting here. So this is minus ddu of delta x minus xn of u. Okay. So ddu acts on one of the 4 delta functions. Okay. But now you see you have a sum of over all 4, right? And as you sum over all 4, ddu acts in turn on one after the other. So this I can rewrite as sum over n en integral minus infinity to infinity du and then minus ddu acting on this is the total derivative, right? With respect to u. So I can do integration by parts. Because this is integral minus infinity du of something. So this I can write as minus sum over n en product mu equal to 0 to 3 delta x minus xn mu of u between u equal to minus infinity and u equal to infinity. X mu, thank you. N, yes. Right, because ddu of this whole thing. And now the idea is that for any finite x naught, this thing is 0. Why? What is xn naught at infinity? U equal to infinity. That is infinity, right? Because as u goes from minus infinity to infinity, time coordinate goes from minus infinity to infinity, right? Space coordinate base remain static, but the time coordinate goes to from minus infinity to infinity, right? So at u equal to infinity, all the xn naughts are infinity, right? And at u equal to minus infinity, all the xn naughts are minus infinity. So as long as x naught is finite, right, this delta function is 0. Right? That's the covariant version of charge conservation. Exactly, that's it. For a given point, we can take u limits to be big enough so that the results are 0. Okay. So at least we convince ourselves that in this covariant form, right, the way I have written electrodynamics, okay, it's all internally consistent. Okay, and now we have to generalize it to curved space, right? Because you want to understand what happens to Maxwell's equation in presence of gravity. So in presence of gravity, in local inertial frame, this must be the equation. Right? Local inertial frame is what we call X prime. X prime coordinate system where the metric is eta mu nu and the derivatives are all 0. The first derivative is 0. This is principle of equivalence, right? Okay, because principle of equivalence is in local inertial frame, the equation should look the same. So let's try to write this in a slightly different way. I'll write this as G prime mu nu. I'll write eta mu nu as G prime mu nu because I can G prime mu nu is eta mu nu, right, in the local inertial frame. I'll write this as a covariant derivative because Christoffel symbol is 0 anyway. F prime mu rho equal to minus eta rho kappa. Sorry, J prime. G prime? Oh, G prime. Yes, thank you. Well, I didn't quite want to do it, but you can do it if you want. Right? G prime is eta, right? So it doesn't matter at this stage. Yeah, let's do it. Okay. Now we want to write the whole same thing in the general coordinate system. Okay. For left hand side, there is no problem, right? Because we already know that this transform as a tensor, right? So this combination is a rank 0, 1 tensor, right? Because it has mu and nu are all contracted, so there's a free row index, right? So it's a rank 0, 1 tensor. So you know how it will look in a general coordinate system. So this side is equal to right. Is clear? This side we don't know what it is, because we don't know what how J transforms. Yes, so that will be the inside that will demand that the right hand side is a 0, 1 tensor. So we can define JK that way, right? But the difference from what we had earlier is that for the Maxwell field, we had no idea what it was in general coordinate system, right? Here we have some idea because J prime or whatever J is, right? We constructed J prime in terms of the particle motion, right? Particle trajectories, and that we can describe in a general coordinate system, right? So you can declare that J is a rank 0, rank 1, 0 tensor, okay? But we should be able to find an expression for J, right, in terms of the particles. Okay, so that's what we have to do, right? So as you said, we declared, so this we write as minus by declaring that J is J kappa is J alpha is a rank 1, 0 tensor. Is it clear? Right? In other words, J prime is given here. Let's suppose that there is a rank 1, 0 tensor such that it restricted to the local inertial frame, it gives you J prime. Okay, J prime we know how to construct, right? In terms of particle trajectories we have constructed. So let's suppose that there is some rank 1, 0 tensor whose restriction to local inertial frame is this. Okay. Then we can use the tensor transformation law. If J is a rank 1, 0, then this is rank 0, 1, right? And we are using the tensor transformation law of rank 0, 1. Okay. So you can now strip off this from both sides, right? You can just multiply by its inverse, and we get the Maxwell's equation into G as G beta gamma d beta F gamma alpha equal to minus G alpha beta J beta of x. Is this step clear? This is an input, right? J is a rank 1, 0. Yes, we are just declaring that we will define J in a general coordinate system in such a way that it's a rank 1, 0 tensor. Same thing we did for the F. Same thing we did for the F, right? But here we have to do a little more work because we want to be able to calculate J in terms of the particle trajectories, right? in a general coordinate system. Because in the local inertial frame, right, we could calculate J in terms of particle trajectories, right? So you should be able to do it also for in a general coordinate system, right? It shouldn't be, okay, you can say, okay, we take the viewpoint that whenever you have a particle system moving, right, at every point you go to a local coordinate system, find what J prime is using the standard formula and then change back coordinates, right? But that's not a very efficient procedure, right? We would like to have a direct expression for J given the particle trajectories in a general coordinate system, right? Exactly. So what is the Card space analog of the thing we did, right? That's the question. Is that clear? And the Card space analog of that formula is what we are looking for. So from this, we know that J alpha of x will be given by because that's how you have declared J should be, right? J transforms as a rank 1, 0 tensor. So we are now going to substitute that expression that we had found for J prime mu x prime in this expression. So this is all these are prime. Okay. Now this is evaluated an arbitrary point in space, right? We can bring it inside, of course, right? Inside the sum. Nobody can prevent us from, let me do that step. En integral minus infinity du right? This doesn't depend on n, right? I can always put it inside. This combination can be given a simple interpretation because of this delta function, right? See this, because this delta function tells us that it's only relevant inside the sum, right? This has to be evaluated when x prime is equal to xn prime. Right? Using that, we can rewrite this, right? What is it? So this becomes dxn mu of u du. Right? It becomes this because of the delta function, right? Otherwise, this is evaluated an arbitrary point in x. But inside, once you have brought it inside the sum, right? The only place where this is relevant is that you have to evaluate it on the trajectory. Right? And when you evaluate on the trajectory, then this is dxn mu du. Is this clear? Right? Because you are just expressing x mu in terms of the x prime coordinate, right? To go from here to here. So this part is good, right? You have gotten rid of the x prime coordinate and written in terms of the x coordinate. So what else do you have to do? This Dirac delta, right? There is x prime sitting here. When you convert it to x coordinate system, right, then by construction, when x prime is equal to xn prime, x is equal to xn. Right? It's the same coincident point, right? You are just describing everything in the unprimed coordinate system. So this Dirac delta function, we can also write as delta 4 of x minus xn of u. Almost. There's a Jacobian, right? Because delta of fx, if you remember, right? Suppose fx of it has a single zero, right? Then this is delta. Suppose fx has a zero at x naught. Delta of fx is delta of x minus x naught times 1 over f prime of x. Right? This is our Dirac delta function transforms. Right? Delta of x is equal to 1 over a times delta x. Right? That follows from the definition that you have to once you integrate over x, you should get 1. X naught. Thank you. Well, I didn't have to put x naught because this delta function is there, right? But okay, let's put x naught. It's important because you will not do that. I mean, when I write the next step, right, I'll not put that x naught in, but the delta function will do it. Okay. So now here you have product of 4 delta functions, right? And each of the x primes can be a arbitrary function of the other x's. Right? But fortunately, there is a formula. Okay, the analog of this formula when you convert this to this. Okay, you have seen that formula. There is a determinant of the Jacobian that comes. Okay, so the claim is that delta 4 of x prime minus xn prime is equal to delta 4 of x minus xn of u times 1 over determinant of okay, so this is a matrix. X prime is a function of x. Right? This is a matrix. Okay. You have to take the calculate the matrix. So it's a 4 by 4 matrix. Right? Take the determinant of that. Right? And that 1 over mod of that is what going to come in the denominator. Right? This is the analog of this. If you think of this as a 1 by 1 matrix, right? A single change of variable. Then you take the derivative of whatever is inside with respect to whatever the variable you are changing to. Right? And you put 1 over that in the denominator as a multiplicative factor. Yeah, but that non-singular coordinate transformation will have that problem, right? Because we have been assuming that the coordinate transformations are non-singular. But it's still not very satisfactory, right? Because you have knowledge about the x prime coordinate. Right? We don't want to have any x prime around, right? Because this means that you have to first find the coordinate transformation that changes to a local inertial frame, calculate the determinant, and then put it in, right? That's not a very efficient thing to do. So you have to find out somehow a representation of this in terms of something that is measured purely on the x coordinates. Right? We don't want to have a reference to x prime coordinate system. Any suggestion how to do it? Yeah, but it will still have the x prime, right? We have to get rid of the x prime somehow. Yeah, so the point is you use the transformation behavior of the matrix. Okay, because this matrix comes in all tensor transformations, right? Okay. But a general tensor, we don't know either the right hand side or left hand side, right? So it's not very helpful. Okay. For the metric, right? Let's see what is special about the metric. Okay. Metric transformation will have this matrix, right? Because it's a tensor. Okay. But metric has a special feature that G prime mu nu you know is eta mu nu, right? So that's what we're going to use. Okay. So let me explain what this is doing. Okay. Yes, roughly yes, right? Because in terms of eta mu nu, the distances were measured in flat metric, right? In the new RB general coordinate system, right? Locally you are just scaling, right? X and X prime, right? You are changing, stretching it, right? That's why the metric is different, and that knowledge is what we are going to use to express this in terms of the purely X coordinates, defining the stretch. Okay, so use the fact that okay, you have to get the sigma in the denominator. So G mu nu is and this is eta rho sigma. Right? So let's try to write this in the matrix notation. Okay, so let's say that we define S mu rho as del x prime rho del x mu. Then this can be written as, let me write in the matrix, G mu nu is equal to S mu rho G prime or eta rho sigma. And here you have S mu sigma. Right? Thinking of the second, this shift, this is just a notation, right? But now we're going to think of this as a matrix. With this as a row index, this as a column index. Okay. And so you see that here the column index is contracted to the row index, which is okay. Here the column index is contracted to the column index. Right? So it's not quite the matrix product, but you can transpose it. Okay. So this I can write as a matrix form. G is equal to S eta S transpose. Right? Because S transpose, because the matrices are not quite in the right place, right? Because when you take a transpose, sigma becomes a row index, and then it's contracted. So determinant of G is determinant of S square, because S and S transpose have the same determinant, and determinant of eta, which is -1, is -1. Oh, because if you have A mu rho, I'm just writing everything in the denominator, so this is less confusing. A eta rho sigma, okay, and here you have A nu sigma. Oh, when you take a determinant, right? Determinant of a product of matrices is a product of determinant. Right? That's what you are. Then it doesn't matter. Right? Once you are taking a determinant, it's just a number. Right? So then I can write it this way. Okay. So this tells us that determinant of S is minus square root of minus determinant of G. Okay, and you take the positive square root because we have a mod here. Is it clear? So with this, I can now write this as delta 4 x minus x of u times 1 over square root minus Is this clear? Yeah, in 4 dimensions it is always -1, right? But in another dimension it could depend on a signature, right? If you had 1 time 4 space dimension, for example, then if you take time to be 1 and space to be -1, then the determinant will be 1. Yeah, but if you take 1 time with the time, if you put a -1 on the time, then it's always -1. Is this clear? Okay. So this then lets us write the expression for J mu purely in terms of quantities at x. We get J mu of x as sum over n, En integral minus infinity. Okay, this one has no knowledge about the x prime coordinate. Okay, and you can easily convince yourself that if you now change the x coordinate to some x double prime coordinate, it actually transforms as a tensor, right? Basically, what will happen is that during the transformation, this will become a Jacobian from x to x double prime, but this will also become a Jacobian, right? And those will cancel. Okay. And then this satisfies d alpha g alpha of x equal to 0. Okay, that also follows from the fact that this is a scalar, right? So you can evaluate it by going to the local inertial frame, and there you know that it's 0, right? So it better be 0 in a general frame. So this basically completes the construction of the charged particle coupled to Maxwell field in the presence of gravitational background, right? If you want to know that if there is a gravitational background present, okay, and if there are charged particles moving around, right? How does the Maxwell field, what equation determines the Maxwell field and what equation determines the motion of the charged particle? Okay. So next time we are going to start with the other side of the question, right? That imagine that you have a set of particles moving in a gravitational, moving around, right? What kind of gravitational field does it produce? Right? There, we cannot rely totally on principle of equivalence, because if you go to a local inertial frame, there is no gravity, right? So obviously there is no equation that tells us how to determine the equation for gravity by going to a local inertial frame. Okay. So what we have to rely on, okay, it will not be a derivation, it will be a guesswork. Okay. And in that guesswork, we will basically rely on what we have learned from electromagnetism, right? The fact that we need a source, right, which is conserved, right? That is something that we'll be using, right? We'll use the fact that Newton's laws, okay, it should somehow reproduce Newton's laws in appropriate limit, and we'll use the fact that Newton's laws for that determine gravitational field in terms of the particle distribution is second order in derivative, right? The gravitational potential is satisfies the Poisson equation, right? The del square phi equal to the mass density is proportional to the mass density. Right? So that suggests that even in the in general theory of relativity, right, you should look for an equation that involves two derivatives of the metric, right? Because the metric, as we saw, is directly related to the gravitational potential. Right? So those are the insights you have to use to figure out, okay, what could be the form of the equation that determines the gravitational field in presence of matter. Only in the non-relativistic approximation, right? If you remember that we saw that in the weak field limit G00 is eta 00 plus something proportional to V, right? Some constant times V, which is the gravitational potential, right? I think this is what we call V. So that insight you have to use, because we do want that in the non-relativistic limit, you should get back Newton's theory, right? Because it works quite well. But after saying this, let me just again emphasize that we will not be able to derive it, right? Because there's no principle of equivalence, right? We only have to use these insights to guess what the equations could be. Okay, the equations that determine the gravitational field in presence of matter. Exactly. It should be consistent with this uncertain limit, and from the general principle that whatever appears on the right hand side should be a conserved quantity, right? In a sense that we'll be describing. Right? So those are the insights we are going to use.
Are these things sufficient for us to have?
We'll see. We'll see to what extent, I mean, we can determine this. Right? Again, I mean, I'm not again trying to claim that this is a unique way, right? If you put enough number of constants, indeed, there's a unique solution. Right? There's a unique equation that you can write down. Right? But we have to put enough number of conditions. Without that, you will not be able to determine the equation uniquely. Okay, so I think I'll stop here and continue tomorrow. That you can always do. So once you are parameterized, right? Suppose you want to eliminate U numbers. We just get it's not exactly. Suppose you say that x is not of u is equal to x naught, right? That's the time. You can use this to solve for unit numbers. Yeah, that you can always do. Right? So you can always go back to the original form in which time places present. Right? You specify the coordinates. Yeah. Exactly. I mean, this is the equality because xn naught is supposed to be the time coordinate of the particle. Right? That cannot be equal to that. And see what it becomes in the code. Let me give the simple example of the party part. That we started it. We demanded that this was the form of the equation in the after that we demanded code. Just say the next leg is x and time and write in the general code. And then you go to now, right? This is the general coordinate system not yes. So it is. But the point we didn't demand. It is because we are saying that all equations in general coordinate system come from coordinate transformation of this system. It automatically is covariant because any equation that we get, right, the cost convert to this and then come back again. That's it automatically. Yeah, it is unique, so you don't have to. That was a shortcut of that. Right? You didn't have to do that. You start from this. Okay. Start from that, and then you use the fact that the convert these into this partial rule, right? And similarly, every time you have declared to be covariant, so this is the substitution. It automatically give you that. So it's not that I mean we have to take any item. Right? We just do a brute force. What I gave was a shortcut answer. Why it should. So what you'll do, I mean, if you do this, what you'll find is that these terms all cancel. So you could have written the equation also in terms of this ordinary derivative. But this, if you replace this by covariant derivative, right? Gamma all cancel. You can rewrite the same equation with covariant. And that's a special property because of this total anticipatory mean. So you can also write the equation this one, but this is entirely equivalent to writing the equation. The advantage of writing it this way is that you don't need to invoke any anticipatory. It's an anticipatory. It's also covariant because it's equivalent. Over 0